of solutions. It's basically the Faulkner-Scan transformation to develop self-similar solutions for wedge flows. Okay. So the solutions can be of different types. Let me see. So if you look at it here, for example, okay, so this is one type of a wedge. Go to the PPT view. Okay, so this is one type of a wedge. Okay, so the angle subtained is beta pi. Okay, this is one type. Okay, so this is u infinity still t infinity. This is how the direction of x is actually measured. Okay, so this is more like a convergent channel kind of a flow. Whereas the other part that you see, this is also another wedge, okay, where the flow is a little bit diverging. This is minus beta pi. Okay, so the flow, this is the direction of x. It is still u infinity t infinity. Okay, and the angles, these angles can go. It can be anything that you want. Okay, so when it becomes flat like this, it becomes a Hyman's flow. Okay, when the angle goes to 0, it becomes basically the flat plate boundary layer. Okay, so in between, and when it goes to the other extreme, basically crosses the 90-degree mark, you get these kind of solutions. Okay, so the Faulkner-Scan class of solutions basically is applicable for any type of wedge where the incoming flow is always uniform in terms of velocity and temperature. Okay, so based on this, let us go back. So first and foremost, the first assumption assumption 1, u infinity is equal to C1 x to the power of m. Okay, where does this come from? We promised that we will cover the origin of this. It basically comes from the potential flow theory. Right, outside the boundary layer, okay, the potential flow theory dictates that C1 must be equal to u infinity should be equal to C1 x to the power of m. Similarly, t minus t naught minus t infinity, where t naught is the temperature of the wall, okay, is given by C2 x to the power of n. Okay, n and m are different as of now. Remember that. Okay, here we try to establish the relationship between the two. M is equal to beta by minus 2 by beta, 2 minus beta, where beta greater than 0 implies that the flow is accelerating. That means it's like a channel flow. Okay, beta less than 0 implies the flow is decelerating. That means it's basically a diffuser kind of a flow or a divergent nozzle. Beta equal to 0 implies a flat plate. Beta equal to 1 implies a stagnation flow. So you can see the corresponding m's you can find out from this particular thing. One thing you can notice is that when beta is equal to 0, m is also equal to 0. So flat plate basically corresponds to m equal to 0. Does that obey with this? Because as you put m equal to 0 in this particular expression, your u infinity becomes a constant, which is the correct thing, right? For a flat plate with no inclination, your u infinity, that is your free stream velocity, is not a function of x, right? Okay, so that is easily, you can see that that is the condition over there. Okay, similarly, m is also equal to 1 when beta is equal to 1. Okay, got it? So m equal to 1 because beta is equal to 1. That would mean that u infinity should be equal to C1 into x, right? So that would mean this type of thing, if you recall your fluid dynamics or viscous fluid flow, this actually typically corresponds to a stagnation type of flow, right? So this kind of agrees, whatever our strategy was, is kind of agrees with the view that we have linked it with beta, where beta is basically the wedge angle, right? Okay, let us, based on this, let us try to see how we can actually best define the whole framework once again, the self similarity solution, because that is what we promised. Okay, So, neta is equal to y over delta to y u infinity by gamma x, u infinity is equal to C1 x to the power of m, neta is equal to y into C1 by gamma x m minus 1 by 2, right. Okay. Psi, which is basically the stream function, this we already defined in the general case of suction and blowing. Some parameter space like this, right. Now, let us do the transformations. D psi by dx is slightly different of how we progressed with the self similarity solution with a flat plate, but we could have done it also in this way. So, there are different routes, essentially the thing remains the same, you are free to use whichever one you are most comfortable with. By d neta by dx, d psi by dx. Okay. Now, neta is given as y C1 by gamma x m minus 1 by 2, right. Okay. This is also given. So, therefore, this leads to, these are all mathematical transformations. So, it just requires that you just work out the math, okay, in more details. Which gives you got it. So, d psi by d neta is equal to okay. Similarly, d psi by dx equal to okay. So, this is after this, okay, after this. So, these are the different types of transformations that we are actually doing over here, okay. So, similarly, d psi by dx. So, this is the stream function approach to the similarity solutions. The flat plate can also be done in a very similar way, but we chose to show two approaches in two problems so that you can adopt any one of them, okay. So, therefore, d psi by dy okay. So, now we already know this is your u. So, therefore, this will be okay, and u is basically equal to u infinity f prime neta. So, you can see that it kind of agrees we started with this particular expression first, right, in our previous approach. You can see that these two things are basically equivalent to each other, right, except u infinity instead of a constant, now it is C1 x to the power of m now. Given by that, if I write the full expression, because there are a few steps which I am going to skip over here that you can work out. This is what we wrote in our general case of suction and blowing also. This comes basically like this. Okay. Now, if we can do a check, if m equal to 0, which is basically the flat plate boundary layer, your V becomes equal to u infinity into gamma by x into half minus neta df by d neta. So, this is correct, right, this is quite correct. Okay. Now, to go to the momentum equation, we need to find out terms like du dx plus du dy, d square u dy square, etc., etc., right, all those things needs to be found out. Okay. So, let us write du dx is going to be long because we are carrying a few terms with us now. Okay, f prime plus c1 is equal to got it. Okay. So, that is du by dx. We are doing it term by term so that we can collect it at the end. Okay. Du dy will be equal to okay. So, that is the first derivative. Similarly, okay, that is the other term. Okay. Now, we feed all this information to the conservation of x momentum, which is basically u du dy plus v, sorry, okay. Here of course your pressure term dp by dx is minus u infinity du infinity by dx, right. This comes from the Eulers. Right. Okay. So, now what we do is now you put all these values of u, v, du dx and all these values, and the final form of the equation therefore, now it is term by term substitution. Okay. So, that is the total expression that you got. okay, in this particular. Okay. So, as you can see once again, if m is equal to 0, what will happen? Okay, this equation will become 2f triple prime plus f into f double prime. This entire term goes to 0. So, you will get a 0 over here. So, this will lead to f triple prime plus half f by f double prime is equal to 0, which is like the flat plate boundary layer equation. Okay, we once again get the same thing, the flat plate boundary layer. Okay, but this is the total expression when you actually have a wedge solution. Okay, so this is a general class of solution, more generic than your Faulkner, than your Blasius boundary layer. Okay, so the boundary conditions will be, okay, u equal to 0 at y equal to 0, that leads to u equal to 0 at neta equal to 0, leading to f prime is equal to 0, v equal to 0 at y equal to 0, leads to v equal to 0 at neta equal to 0, leads to f equal to 0, right. U equal to infinity at y goes to infinity, leads to f prime as neta progresses to infinity is equal to 1. These are the sets of boundary conditions that you have. Okay. So, now, okay, as soon as these things are done, okay, so let us now look at, okay, what the boundary layer profiles are going to look like before we go to the energy equation and see what the energy equation should look like. Okay. So, let us look at this particular expression over here. Okay. So, these are for the different betas. This is basically nothing but the velocity profile u by u infinity, right. Okay. So, as you can see, beta equal to 0 once again is a flat plate boundary layer. Let us mark that line. So, this is basically your flat plate boundary layer, right, basically your flat plate boundary layer. In this particular direction, you can see that the boundary layer is basically sagging a little bit. Okay. That is where the point is that your beta starts to actually become negative. Okay. And in this particular direction on the other side, the beta is actually increasing. Okay. So, this corresponds basically to a diffuser, that corresponds to a convergent nozzle, right. Okay. Now, as you can see from a diffuser, what happens, very standard things, as you have a diffuser, what happens is that the flow is basically facing what we call an adverse pressure gradient. As the pressure, as this diffuser angle becomes larger and larger, the flow will at some point of time starts to separate. Okay. And that separation happens at around beta equal to 0.198. Okay, approximately close to minus 0.2. Okay, as you can see, the boundary layer profile is almost equal to 0 because the shear stress is nothing but the slope at this particular point, right. So, as you can see, the boundary layer is sagging, okay, and it is actually equal to 0 at the walls. That means the wall shear stress should be equal to 0 at this particular point, right. So, as you go on increasing the diffuser part, okay, chances of flow separation increases, and as the flow separation increases, you actually have separation of the shear layer. As you have separation of the shear layer, the flow basically therefore separates. On the other side, however, the boundary layer becomes sharper and sharper, as you can see, right. Okay, it becomes sharper and sharper. This is based on the similarity parameter, which is basically your neta. Okay, and therefore the shear stress will also become higher and higher. Okay, so we can write it here, when beta is equal to 0, boundary layer is thin. This is corresponds to the accelerating flow, which is basically the nozzle flow. Beta less than 0 means the boundary layer is thick. This is like a retarding flow, right. Okay, so tau is basically given as du dy at y equal to 0, right, which translates to tau is equal to mu u infinity by x double prime is equal to 0. So, therefore, Cf, okay, should become 0 into Reynolds number to the power of minus half. This is a function of beta. which is quite obvious from this particular graph, that as you increase beta, okay, your u by u infinity profile changes. As a result of that, your f double prime equal to 0 profile also should change. Because of that, you are going to have this kind of thing. Okay. So, this is quite apparent in the next plot. If you look at this, okay, this is flow over a wedge. So, this part is once again the beta, the same thing. Okay. This is like, as I said, flow through a diverging channel, and this is the flow over a wedge, right. Okay. So, as you can see that this is basically nothing but your shear stress, the wall shear stress. This is your f double prime equal to 0. As we saw, Cf was proportional to this, correct. So, we can see in this particular case at 0, this is what is whatever the value that is you get from your self similarity solution. As you go to about point minus 0.2, okay, everything separates and you basically get 0 shear happening over there. Beyond this, there is separation. Here, of course, you can see that the shear stress will continuously increase. So, it is very much like their suction and blowing kind of a stuff, except that here the boundary layer thickness is varied just by changing the channel wedge, that whatever is a wedge angle, we are varying that and we are able to get this extraordinarily nice profiles coming out of this. Okay. So, based on this, okay, we can certainly say that Cf will be reduced, is reduced as beta is reduced, right, becomes Cf is equal to 0 at the point of separation, right. At the point of separation, Cf becomes equal to 0. So, from this particular profiles, that what we have done over here, we saw two important things is that when the flow is accelerating, the boundary layer is always thin. When the flow is decelerating, the boundary layer is always thick. Okay. So, that is proven through this analysis, and the shear stress, which is dependent on the profile, the boundary layer profile essentially, or basically the angle at the wall, that also changes, okay, with the wedge angle. Now, coming back to our journal. So, therefore, we can readily see the estimates that wedge flow is self similar, right, is self similar, okay, and Cf is actually given by f double prime 0, which is a function of beta that we saw. As beta goes up, or rather beta comes down, Cf also comes down, right. Cf is equal to 0 when beta is equal to minus 0.198, okay. Cf goes up when beta goes up, right. So, these particular things, and if you look at what we did, all these mathematical calculations, okay, yielded that this is the basic governing equation, right, which we basically solve in a very similar way that we did earlier. That means using the shooting scheme and things like that. But even without the shooting scheme and without all these things, the basic problem remains that the solution pattern remains the same, except that the boundary layer is accordingly modified depending on whatever is the value of this m going to be. That means whether it is, this m is nothing but your beta, remember m is your beta actually, okay, and the special forms can all be derived from this particular expression, right. So, we are left with, in the next class what we are going to do is that we are going to look at the energy equation now, okay, because the energy equation comes after this. Now, we have solved the momentum, we know how it looks like, we have explained what is the nature of this profile is going to look like, but we are going to see that through the energy equation what we can get, that whether the energy equation is any different or whether it predicts something very similar, that also we will see by looking at the results. Okay. So, in the next class we are going to go into the energy equation mode, but the wedge, now it is very clear that how we got those equations in suction and blowing. Okay. Suction and blowing physically kind of represents the same thing as your wedge solution. It is all about changing the boundary layer, thickness of the boundary layer. If the boundary layer profile changes, everything changes, right from your shear stress to your wall heat transfer coefficient. Thank you. Solution, we looked at the momentum part, now it is time to look at the energy part of the equation. So, the energy equation can be taken as, okay, theta is equal to t minus t naught by t infinity minus t naught, that we said earlier, right. T naught minus t infinity is basically given as C2 x to the power of n. We do not know the functional form because they may not have the same functional form as your velocity. Okay. So, therefore, T naught rather T is given as T naught plus C2 x to the power of n 1 minus theta, right. Okay. So, dt by dx is equal to C2 into n x to the power of n minus 1 minus theta plus C2 x to the power of n minus d theta by d neta into y C1 by gamma m minus 1 by 2 x into m minus 3 by 2. Okay. Okay. So, it becomes equal to C2 x to the power of n minus 1 n into 1 minus theta neta m minus 1 by 2 okay. Similarly, your dt by dy, if you do follow the same course of math, d theta by d neta u infinity gamma by x. Okay. So, you understood what we did. Okay. So, it is pretty much just substituting u infinity as and when it is required, right, because remember u infinity is still given by C1 into x to the power of m. That is how this m comes into the picture, right. Okay. So, similarly, delta square t dy square is given by C2 x to the power of n d square theta d neta square u infinity gamma into x. Okay. Now, once again what we need to do, because your energy equation is dt by dx plus v dt by dy is equal to alpha delta square y by dy square, correct. Okay. So, we already have evaluated this. Okay. We have already evaluated this, we have already evaluated this, and we already know what is a functional form of u and what is a functional form of v from our earlier momentum analysis, right. So, it should not be a problem. Now, what we do is now put all these terms together, okay, because the new terms we have already evaluated in the same way that we did earlier. Okay. So, the final form becomes let me just okay. Now, if m is equal to n equal to 0, typical flat plate boundary layer solution, okay, what we get is theta double prime this equation will boil down to this particular form, which is the correct one, as we already know from our other analysis. Now, if n equal to m, that means the temperature and the velocity, external temperature and velocity has got the same functional form. Okay. This equation will now become theta double prime plus half Prandtl number m plus 1 into f theta prime is equal to 0. This is the expression that we also used in our suction and blowing. So, your Nusselt number will be equal to theta prime 0 into Reynolds number to the power of half. Here what has happened is that Prandtl number has been substituted by Prandtl number as m plus 1, right. So, it is like a pseudo Prandtl number. Okay. So, Eckert actually integrated this. Once again, this kind of thing has to be solved by knowing what is the functional form. Integrated it with theta 0 equal to 0 and theta infinity is equal to 1. Okay. So if you look at the presentation format once again, okay, so this is basically the expression, okay, and the line that it's given as a solid line, okay, that is basically the correlation that you are most experienced with, okay, is plotted with terms of Prandtl number, okay. So as you can see in this particular configuration, once again you have beta equal to 0.5 and n equal to 0, beta equal to 0, n equal to 0.5, okay. So these are, don't be bothered about the constant heat flux and the constant boundary profile, it's not the point over here, but you can see that this is plotted with respect to your Prandtl number, okay. So Prandtl number greater than 0.5, the correlation works pretty well, okay. Basically this 0.332 into Prandtl number to the power of 1/3 correlation works pretty well, okay. Here also can look at table 2.3 of Bejan, okay, in order to see that what is the solution for theta, okay, what is the solution for theta for different m, okay. So that what we are going to do in the next class, we are going to give you a chart in which we are going to say that this is the table which contains all the values, okay, of beta, okay. So based on this, okay, based on this we have pretty much finished the case of Faulkner scan, with the exception that I will provide a table which may be which will be added with this particular class, where we will say that what is the basic case of basically suction and blowing, what is the m parameter all about, right, okay. Now without in order to finish off the external flow, okay, there is one more thing that we need to address, which is called the arbitrary wall temperature. That means this is a very specialized case, and I will show you what that specialized case is, okay. Say for example this is your generalized flat plate, okay, this is how the boundary layer actually develops, okay. So say in this particular portion between x1 and x2, okay, between two limits of this particular profile, okay, the temperature is Tw, where Tw is greater than T infinity. On the two sides of the plate, this is still T infinity, understood. So it is a plate in which only one segment of the plate is actually at a higher temperature than the incoming flow field. The other part of the plates, okay, are at whatever temperatures. In this case it is the same as the ambient, okay. So if the temperature was the same as the approaching temperature, you know quite well that there will be no velocity profile will be developed, right. There will be no velocity profile that will be developed if the profile is the same, right. But however in this particular case there is one section where the temperature is a little higher, right. So it is almost like this, in this particular section the temperature is higher, exactly like that, okay. So what you are going to have if the plate was heated from x1, right, say entire plate was at a temperature Tw, right, you would get a boundary layer which will start developing from here, right, okay. Similarly if the plate is it's heated from x2, you will actually have a velocity have a thermal boundary layer which will develop from there, right. Let's call it delta T1, this is delta T2, correct, okay. So you note one thing, one important thing when you solve this particular problem, that the integral energy equation that we did, right, energy equation is linear in temperature, isn't that so? It's linear in temperature, okay. Hence to solve this particular problem we can apply the method of superposition, okay. We can apply the method of superposition. Superposition is allowed for a given velocity field. See, the velocity field is unaltered, right, because it's a one-way coupling as we said. That means the change in the density has got no effect on the temperature. So the integral energy equation is linear in temperature, and we can apply the method of superposition, okay, because it's linear. We can apply the method of superposition provided we know what is the velocity profile going to look like, right. So this is the way, say for x1, this is one of the velocity profile, one of the temperature profile, this is the velocity profile, right, that develops regardless, right, that is delta, right. So this is the first temperature profile, okay, where this is TW, okay, which is a plus delta T effect. Delta T is basically T wall minus T infinity, okay. I am summing it, okay, with this particular profile. Once again this is still delta. Now it is x2, right. This particular profile has got a temperature like this, right, which is delta T2. Now this temperature I am taking it as minus delta T, right, because here we have a plus delta T added throughout the length of the plate, right, with plus delta T throughout the length, but in reality only the portion x1 and x2 is the only portion that is heated. So therefore from x2 if we take a profile which is minus delta T, then basically you are taking into account the effect of that, basically you are subtracting that effect out from the whole picture, right. So therefore if this is the situation for x1, x greater than x1 less than x2, H will be given as k by x into 0.332, Prandtl number 1/3, Reynolds, this portion remains the same regardless, right, okay, 1 minus x1 by x to the power of 3 by 4 to the power of minus 1/3, okay. 1 minus x1 by x to the power of 3 by 4 minus 1/3, q double prime is h into delta t, that is given as k by x 0.332, Prandtl number 1/3, Reynolds number half, delta t 1 minus x1 by x to the power of 3/4 raised to the power of 1/3, okay. This is for this region, right, for x when it lies between x1 and x2, right. For x greater than x2, right, your q double prime becomes k by x 0.332, again Prandtl number 1/3, Reynolds number half. Now it becomes a little bit more complicated, okay, because now you have the effect of the previous one as well as now you have this minus delta T effect as well, right. So it is 1 minus x1 by x to the power of 3/4 to the power of 1/3 minus 1 minus x2 by x, sorry, three-fourth raised to the power of 1/3. This entire thing is multiplied by delta T, okay. Let me write it maybe in a more proper form. So q double prime is equal to k by x 0.332, Prandtl number 1/3, okay. So that's the expression that you get in together, okay. So is basically a reabsorption of heat in the heated section, okay. Now if there are n such step changes, it's possible, right, you can have n number of step changes, right. So you can have situation like this, right, x1, x2, x3, x4 like that continued, okay. So you can have step changes like this, you can have any combination that you want, right. So if there are n step changes. It becomes a summation now, okay, I equal to 1 to n delta Ti 1 minus xi by x to the power of 3/4 1/3, okay. This is the step changes. So, you can add all the steps depending on whatever it is, like delta T1 is negative, positive, you can do it in whatever way that you want, right. Okay, now if there is a smooth variation, Q double prime will be given as 0.332 k by x, Prandtl number 1/3, Reynolds number x to the power of half 0 to x dt 0 by d neta by neta. This is the dummy variable, okay, 1 minus neta by x, this is only raised to the power of 3/4 and add 1/3 to the top of that, right. So, this actually shows you that this is how for any type of temperature profile, that means if there is a variation in the temperature profile that we have across a plate, you can actually represent it in this particular fashion, right. Now, what to do if there is a similar situation in which we have a uniform heat flux kind of a consideration, okay. So, how to add those things also, okay. So, that will take a little bit of time. So, what we are going to do is that remember last class we actually posed that what happens when there is a uniform heat flux situation, right. If you recall, that is what we did in the last class, where we said that if there is a uniform heat flux, the integral formulation, how it can be done. Do you recall that that was what we actually did? Now, if that is the case, what we are going to do in this particular class or in the next class, that we are going to look at that particular solution. Hopefully, you guys have already done it by now. So, you can cross check that what will be the answer. But in any case, if there is a, let me just give you the general profile for a uniform heat flux consideration. When there is an unheated, again there may be an unheated section, right. This is delta still goes up as it is, okay. From x1, okay, you are pushing in a uniform heat flux, right. Let us call that Qs double prime. So, you are pumping in a lot of heat flux, okay. After say not x1, say it is x, this distance is say from here to here, from here to here is x naught, right. Now, this is no dissimilar than the problem that I gave you where the uniform heat flux was everywhere, right. So, in this case the answer will be, the Nusselt number will be 1 minus x naught by x raised to the power of 1/3, Prandtl number 1/3, Reynolds number x to the power of half, right. When x naught is equal to 0, which is the case, which is the exercise that I gave you, okay, the Nusselt number is 0.147, Prandtl number 1/3, Reynolds number x to the power of half, right. Now, in the next class we are going to look at how we got this before we wrap up this particular section, right, that how we got this particular profile, because we did it only for uniform wall temperature. I gave this as an assignment. So, we are going to do it in the next class and show that how this thing actually works. While on the other hand, for any unheated starting length, this is the form that you are going to use, right. That means if there is an unheated starting length, a portion of it there is no heat. So, in that case this is the profile that you have to follow, right. So, this actually completes. So, what we are going to do as a part of this lecture, we are also going to show you that table which shows that how the Nusselt number and other thing varies with m, okay. So, that is still remaining that we will add, okay. But in essence the entire external forced convection is kind of complete, with the exception that we are going to just do the uniform heat flux case, which were given as a homework problem. I am going to just do it here so that you can cross check that whether you are on the correct path or not, okay. So, using this is where we wrap off. Okay, we are going to look at internal forced convection from next class onwards. So, just to add, as I was stating that if you look at that when there is a flow over a wedge, we wanted to know, for example, what will be the local Nusselt number values, okay, and that is exactly what we are putting up over here. So, if you look at the at this list, okay, so this is your beta, the one that we said is the wedge angle. This is the corresponding transform variable, which is m over here, okay, and these are the different Prandtl numbers. So, this is Prandtl number less than 1 regime, this is Prandtl number greater than 1 regime. So, as you can see, beta equal to 0 corresponds to the flat plate situation, right. So, Prandtl number equal to 1 is 0.332, as we knew earlier from our similarity transformation. So, this is for different sets of Prandtl number, what are the different values that you get, okay. So, similarly m equal to 1 basically corresponds to the Hyman's flow condition or the stagnation flow. So, those values are also given over here. So, as you can see, the Nusselt number seems to be a function of the Prandtl number, okay, for all the wedge angles. But as you can see that as we increase the wedge angle, okay, that means you are going into a more and more convergent nozzle kind of a situation. That means the flow is accelerating a little bit more, okay. You can see that the value of your Nusselt number correspondingly increases, right. So, this is kind of obvious, the same reason that we explained earlier, that when the flow is accelerating, you have a very thinner boundary layer. So, that means your Nusselt number or your heat transfer coefficient should actually go up, right, because it is inverse of delta T, right. So, this is what you have an increase in the Nusselt number as you go on increasing the beta. So, this is what I wanted to show you guys, okay. And this is once again the same table, okay, when you actually have suction. All these are taken from Bejan. So, you can take a look at Bejan and you can see that you can study these different types of tables. For example, here of course, what we have done in one particular table, you have the Nusselt number, you have the skin friction coefficient, and this is have the blowing, okay. This is of course over a permeable isothermal plate. There is no wedge angle over here, okay. So, wedge angle is 0. Okay. As you can see that suction and blowing, how does the Nusselt number values varies, okay. You can easily see that, okay. So, as you know, when it is suction, the boundary layer is pulled inwards. So, naturally you have an increase, okay, and it is pulled out, it will go to 0 at some point because of separation. So, this is basically separation all around, okay. Similarly, for an isothermal edge, okay, if you have suction and blowing, that part we did not cover in details, but this table you can still study, okay. So, why some of the data are disjoint? Because not all the experiments were done, not all the analysis were done for all the cases, okay. So, that is precisely what it is. So, it is a wedge where you can actually have suction or you can have blowing. So, that kind of a situation, okay. So, all the data are basically compiled over here. Once again, if you look at the class of the data, you will see that obviously they also make the same sense, because here you can see this actually decreases, okay, for the same reason, because your blowing is actually increasing, correct, okay. For any given condition, you take any set, any m in this particular series, you will find that it is actually going down, okay. So, the wedge, we already know what the wedge angle does, right. On the top of that, if you have suction or you have blowing, you are basically additive or subtractive kind of an effect, okay. So, that is what is happening. Moment you have blowing, you reduce the Nusselt number value, because you are increasing the boundary layer thickness in a relative basis, on a relative basis. For example, this is the boundary layer, this is the Nusselt number for no blowing. If you look at this part of the thing, right, as you go on increasing blowing, this actually reduces, okay. How much it will reduce, that depends on the calculations, that depends on the boundary layer profile. This is done for only one Prandtl number, you can do the same for other Prandtl number also. Prandtl number of 0.7 is roughly equal to that of air, okay. So, that is how this thing has been constructed. So, we end this particular lecture where we actually have shown that with wedge, okay, what are the different values of Nusselt number, because we cannot solve the equation exactly. So, we have to show you the end results, okay. And also we have shown that, for example, when you actually have suction or blowing, what will be the values of the Nusselt number, and when you combine these two effects together, suction and blowing and wedge effect, then what do you get? Okay, so all these things are kind of narrated in the table form, and all of them make common sense. Whatever we argued about the boundary layer, all of them make sense when we actually solve it, and the value seems to agree with our intuitions. Okay, so we end this. Before we now, in the next lecture, we will go to internal flow, internal forced convection. Thank you. This will be the first lecture on internal forced convection. So far we have done external convection. So, the external convection does not have any imposed length scale associated with the thing. Now, in internal convection, we will see that there are certain things which makes it a little bit different from internal convection, internal forced convection. So, the first thing that we are going to look at is basically laminar duct flow, duct or pipe flow. Okay, it can be a channel, I mean like two parallel plates. So, if there is a flow going through it, okay, it can also be a pipe with a flow going through it. It can be varieties of other things. Okay, it can be like this kind of a pipe also. That will be a little bit difficult, that analysis, to do this kind of sections. Okay, there can be a flow through sections like this. There can be flow through rectangular sections, there can be flow through triangular sections, any type of sections. Okay. So, these are all comes under the umbrella of internal forced convection. Okay. So, of course, these things are a little bit difficult to analyze, okay, not impossible, difficult to analyze. So, we will start with a very simple one, again a canonical problem, to show you how things can be generated, okay, and then we will take it forward to the next level. Okay. So, in this particular case, okay, if we have like two parallel plates, okay, and then there is a flow. Once again, this is a uniform flow U, which is approaching the plate, right. This distance between the two plates is basically given by d, which is basically equivalent to the diameter. Okay. So, it can be a pipe also, but the plate is easier because we deal with Cartesian coordinate system, but the same thing can be done for a pipe as well. Okay. So, there is no hard and fast rule about that. Now, so if you look at this particular problem now, the interesting feature is that this is now a bounded flow, because there is a boundary on both sides, right. So, there is no extension to infinity. Also, the moment this flow sees this plates, okay, the boundary layer that we developed earlier will start to develop here as well, right. So, the boundary layer is natural, it is going to happen. That means the boundary layer will be the region where the viscous drags will be important. That means the flow velocity will show a curvature, and so that is going to happen. But now, it will happen symmetrically perhaps from both sides of the plate. That means from this side of the plate also it will develop, this side of the plate also it will develop, right, because there is, we suppose that there is no preferential bias, right. So, as it develops, what happens is that these two boundary layers then merge with each other. So, this is the boundary layer delta, this boundary layer now merges with each other, right. The two boundary layers will merge, because again this is not an infinite reservoir. So, the boundary layer cannot go on extending up to infinity. So, it will merge and basically converge with each other. Okay. So, beyond that, okay, beyond this particular length, okay, you can see that everywhere in the flow the viscous drag is important, right, because the boundary layers have basically covered the entire pipe, duct, whatever you call it, right. So, in this particular section, let us mark this important piece of section. Let us call it something like a xh. Okay. This is of course 0. Okay. So, when x is less than xh, okay, we call this flow to be developing, right. When x is greater than xh, we call the flow is fully developed. Okay. So, we call the flow to be developing and we say that the flow is fully developed depending on what is the value of xh. Okay. So, before xh let us see what happens, after xh let us see what happens. Okay. So, the interesting part will be when you look at this particular section, the section this particular section actually, the developing region of the flow, what do you see that what will happen at the center, that means in this particular region, this is called the core, okay, or in other words it is called the potential core. Okay. So, the name is a potential core. Why is it called the potential core? Because the viscous effects are not important. So, you can apply your potential flow solution which you learned in your fluid mechanics here. You can apply your potential flow solution here, there is no problem, right. Except here of course the potential core does not mean that the flow velocity does not change in the potential core. Flow velocity changes in the potential core, but it does not change due to viscosity. Okay. So, that is what you are getting in your potential core region. Okay. So, in the potential core region there will be a velocity profile which is different from what the velocity profiles are in the boundary layer. After it has merged, that means beyond x by h, right, we can apply the full fledged Navier-Stokes equation to solve it there, right. So, in the developing region there are two parts. Inside the boundary layer it is basically the boundary layer equation or the Navier-Stokes equation. In the core region you apply what we call the potential core solution. Okay. Beyond x equal to xh, okay, the entire thing is basically Navier-Stokes or the boundary layer solution, whatever we will find it prudent over here to apply, right. So, how would the velocity profile actually look? So, let us look at this. Once again we can prove that this will be the velocity profile. So, let us once again draw this profile. This is smooth. Okay. So, in this particular area, as many of you would know by now, the velocity profile is something like this, right. Forget it, this is not at an angle, this is actually all along the axis of the duct. Okay. So, this is a parabolic profile, we will see how it becomes parabolic. Okay. And this profile actually we will find does not change with distance. Okay. So, you can take this profile and put it here, it would be the same. Okay. So, there is no change in the velocity, that is a fully developed profiles feature, that the velocity profile should not change. What about here in this particular section, right. In this particular section what will happen if I draw it properly, okay, you will have that there is a rise from both sides like this, right, and then there will be some kind of a potential core like that, right. So, up to this it is basically the boundary layer, then after that it is the potential core. Okay. This potential core, that means the flat region, right, okay, that will accelerate as you go to the next level. That means this is the profile at x1, if you take another at x2, okay, you will see that this potential core velocity or the velocity at the potential core, there is only one single velocity because the flow is uniform there, it will increase with distance. Okay. And you can readily make out why, that is because as the boundary layers are extending, okay, the flow velocities are changing, right. So, in order to maintain a constant mass flow rate through this conduit, you have to have an increase in the center line velocity, right. Okay. But after the x equal to xh, the velocity profiles will be self similar in nature. Okay. So, some of these things we will prove, so do not worry, but this is kind of intuition that there is an entrance length where the boundary layers are developing, and then there is a fully developed length where the boundary layers do not vary. Okay. So, depending on, so it is not just with hydrodynamic boundary layer, this is hydrodynamic obviously, there will be a thermal boundary layer also which will come in due course, okay, over here. Okay. So, let us do our standard analysis. Okay. and see that if we can extract some scales out of this particular problem. So, at the fully developed region, okay, you know that your delta will scale as d by 2, right. It has to scale as d by 2, right. Okay. Now, in the entrance length, that means in the length where the profile is still developing, okay, if we can apply the equation how does this come? It is the same way as your external boundary layer. This particular terms comes from the pressure. The pressure in the potential code is basically imposed into the boundary layer, right, and this comes from the Euler's equation therefore. Okay. So, the pressure term is substituted by UC duc by dx, okay, and that comes from the potential code solution. Okay. So, now we can do our standard scaling analysis on this. So, the first two terms in this series ux square by x, okay, okay. So, is actually proportional to, okay, got it, okay. So, this will be uc square by x, and the second term, this particular term will be that, right. So, this gives you delta scales as gamma x by uc, or gamma by x gives you gamma uc by x, okay. That is what you get out of this, okay. Now, you already know from your Blasius solution that delta by x is equal to 4.92 into Reynolds number to the power of minus half, am I right? So, that is what you know that is going to happen. You substitute that over here, okay. You substitute the expression for that over here, okay, because this is a scaling argument, that is an exact equation that you got from your Blasius solution, right. So, this is of course not strictly applicable, but we are going to take a leap of faith and use it over here. So, this is Blasius solution for flat plate, got it, okay. Now, in addition to that, we apply one more equation, that delta is equal to d by 2 at the point where the entrance length ends, okay. So, combining these two equations, therefore, you will get x by d will be equal to 0.01 Reynolds number to the Reynolds number d, okay, where Reynolds number with respect to d is actually gamma d by uc. This is not the same as Reynolds number to the power based on x. So, the length scale is just d, okay, instead of that. So, this gives you that your x, that is at the point where the two boundary layers actually join, okay, is given as a function like this, okay. It is given as a form as I have mentioned in this particular equation, okay. This is roughly what we call 1/10, right, okay, of the Reynolds number, right, okay. So, x by d ratio at the point where you actually have the two boundary layers merge, okay, is given by 0.01 of Reynolds number based on d, okay. Now, from the integral formulation we can try to extract the same thing, because this was done rather heuristically, okay, because we just took the scaling from the Blasius solution and kind of applied it here, which is strictly not the correct thing to do, but we kind of got away because these can be constituted as two parallel plates, okay. One plate is at the top, one plate is at the bottom. So, you can consider it like to be two parallel plates kind of independent with respect to each other, okay. Now, from the integral solution, integral formulation, okay, we can apply it directly. Look at this form uc to u into dy plus duc dx. Okay. That is the integral formulation, okay, that we had earlier. From mass conservation, what we can write? Try to understand this particular expression at any point in the entrance length, okay. The total mass is given by this. This is what the mass that is entering inside the duct, right. So, that is rho ud by u, and u is constant. So, this is the total mass that you are flushing in. Now, inside the boundary layer it will be rho u into dy. Just outside the boundary layer it is rho uc into dy, right. So, these two terms when they are added you should give you the final expression. So, this is the conservation of mass, right. There is no ambiguity in this. This is the conservation of momentum, right, the previous equation, okay, where you can also see this is of course u, don't, okay. So, where we have just done the momentum expression in a very similar way that we saw earlier, okay. So, these two things are already kind of known, and it's very intuitive. So, you can assume now, like last time, I am not going through the whole steps because you can work it out yourself. You can assume a polynomial profile and then you can evolve through the boundary conditions, because that is not the intention. The intention is to just give you guys an idea that how this is to be done. So, you can assume very similar to the velocity boundary layer over a flat plate, you can constitute a similar polynomial profile for u by uc in the entrance length, that means in the developing part of the whole thing, okay. So, that you can easily do, okay. So, now applying this particular form into the continuity equation that we have here, okay, what you will get is okay. That is what we have done over here. And now if you just substitute now this into this particular form, you will get this is y squared by delta y cube by 3 delta square 0 to delta plus d by 2 minus delta okay. Now it is easy to integrate 2 delta by 3 plus d by 2 minus delta u by uc d by 2, or in other words u by uc 2 by d by 2 minus delta by 3, then u by uc or uc is equal to u to 3d divided by 3d minus 2 delta, okay. Or in other words, from here you get 2 delta by 3d into 1 minus u by uc, or delta by d by 2 3 into 1 minus u by uc, okay. So, here of course as you know uc is a function of x only. That is the reason we could do such a lot of things, right. It is a function of x only. There has got no dependence on y, because at any particular y section you saw that uc was constant, right. If you do not recall, this is the way. So, if you recall the profile at any particular section, okay. So, this is the straight part. This is what your uc is, right, the core velocity. That is not a function of y, but if you go to a different section, okay, because the boundary layer will be like this will actually, there won't be a sharp kink like that. Okay. So, there will be this UC and that UC is different. So, UC is a function of x, but it is not a function of y. Okay. So, this is what you get as your UC. Okay. And so, this is fairly easy. So, you know that delta by d by 2 is basically 1 minus u by UC. Now, when delta becomes equal to d by 2, okay, equal to d by 2, then 3 into 1 minus u by UC becomes equal to 1, or 1 by u by UC is equal to 1/3, okay, or other words u by UC becomes equal to 2/3. Okay. So, this u then becomes equal to 2/3 of your UC at that particular location, obviously. Okay. So, that is what you get. Okay. Similarly, if you take this particular form, okay, and now do the momentum equation. So, one of the key terms that you need to evaluate in the momentum equation is basically UC minus u into dy, right. So, if you do this properly, it will be UC square. Once again, UC is not a function of y anymore. It will be 2 y by delta minus y by delta square 1 minus 2 into y by delta plus y by delta square into dy, right. Okay. So, if you follow through these steps, if you integrate the whole thing out, okay, and you put that back in your momentum equation, the final form that you are going to get is x by d divided by RED is equal to 3 by 40, 9 UC by u is 2 minus 7 u by UC, 16 ln UC by u. Okay. And this is already, we showed the steps. Okay. So, this is left as a homework. You come from here to here, okay, and this one we have already shown how to do this, all right. Okay. So, you just use this in the momentum equation, you will get this. Okay. There is a little bit of cumbersome math that is involved. Okay. Got it? So, in other words, as we said earlier, so in this case, as you saw, this also UC is actually then 3 by 2 of u. Okay. So, it is other way of writing the same thing. Okay. Now, this particular expression, which is basically the x momentum equation, okay, now if we at the edge of the boundary layer, where we already saw that UC becomes 3 by 2 of u, right. That means the center line velocity becomes 1.5 times the mean velocity. Okay. If we substitute that over here in this particular expression, right, because they all are UC and u, right, combinations of that. So, then this expression yields x by d becomes equal to 0.026 into Reynolds number d, right. This is almost of the same order as 10 to the power of minus 2 Reynolds number. So, what we got from Blasius was 0.01 Reynolds number d, right. So, this is not way off at all, this is of the same order, this is still 10 to the power of minus 2. So, your x by d at the point of boundary layer merger is basically scales as 10 to the power of minus 2 Reynolds number. Okay. So, this is the thing that you should remember, okay, that this is how we got. So, recapping the whole thing, what did we do? We took the integral equation, okay, and the mass conservation equation. Mass conservation equation yielded this. From here we showed at the edge of the boundary layer your UC becomes exactly 1.5 times of the free stream entry velocity. We substituted that in the momentum formulation and we got that these were the expression, which is basically 10 to the power of minus 2 into Reynolds number, which is exactly the same as what we got in terms of our crude Blasius analysis. This is also crude because this is still integral, but we were able to cast it and show that it is approximately 10 to the power of minus 2. Okay. So, as we said, so there are two things that got established. Your UC actually varies with x, it does not vary with y, and UC is actually a lot higher than the free stream velocity u. This is obvious, this is because your velocity you are losing, there is a velocity deficit due to the boundary layer. So, naturally the mean flow or the UC has to accelerate to make up for that. Okay, so that is pretty obvious that, but this value of 1.5 is something that you should keep in mind. This is of course at the edge of the boundary layer, at the edge of the fully developed regime. That means when after this the fully developed regime completely kicks in. Okay. So, through all this exercise we proved that in the entrance length the boundary layer is still growing, UC is still changing, that means the shear stress will still vary quite a bit. After that, in the developed section we will see, we propose that in the developed section the velocity profile does not change at all, okay, at different sections. We will prove that obviously in the next lecture, we will prove that why that is the case, okay, and we will also show that the next we will also say that what happens now to the heat transfer because of all these flow situations, right. Okay. So, this should be now very clear to you that how we got the developing section and how this developing section can be analyzed, okay, and how the flow velocity will change in the developing section. Of course, we will come to the temperature part when we deal with the developing thermal boundary layer. Okay, thank you.